Welcome to this step-by-step walkthrough of Problem 1 from Sensor Systems, Simple Circuit Analysis. In this video, we will break down a foundational two-resistor series circuit using a systematic four-phase approach. Understanding the setup, applying Ohm's law, conducting loop analysis with Kirchhoff's voltage law, and deriving the voltage divider and series resistance formulas. Phase 1. Understanding the setup. In a series circuit, discrete components are connected end-to-end in a single loop. Here, an input voltage source Vin is connected to resistor R1, followed in series by resistor R2 down to ground reference. The output node Vout is taken across resistor R2 relative to ground. According to the principle of conservation of charge, electrons cannot accumulate or disappear at any node in a single path. Therefore, for question A, the current I1 entering resistor R1 must be identical to the current I2 entering resistor R2. Thus, I1 equals I2, which we define as total current I. Phase 2. Applying Ohm's law. Ohm's law states that the voltage drop across any resistor is equal to the current flowing through it multiplied by its resistance. For question B, the voltage drop V1 across resistor R1 is V1 equals I1 times R1. For question C, the voltage drop V2 across resistor R2 is V2 equals I2 times R2. Finally, for question D, the output voltage Vout is measured at the node between R1 and R2 relative to ground. Since ground is at 0 volts, Vout is defined exactly as the voltage drop across R2, meaning Vout equals V2. Phase 3. Loop analysis using Kirchhoff's voltage law. Kirchhoff's voltage law states that the algebraic sum of all electric potential differences around any closed circuit loop must sum to 0. As we traverse the loop from the ground up through the source, the voltage rises by Vin. Moving through the circuit in the direction of conventional current flow, voltage drops across R1 by V1 and across R2 by V2 as energy is dissipated. Therefore, for question E, the total input voltage Vin equals the sum of the individual voltage drops. Vin equals V1 plus V2. Phase 4. Final derivations. Now we combine our findings to derive two key fundamental formulas. First, for question F, we express Vin as I1 times R1 plus I2 times R2. Factoring out the common current, I gives Vin equals I times the quantity R1 plus R2. Solving for current, I equals Vin divided by R1 plus R2. Substituting I back into Vout equals I times R2 yields the classic voltage divider equation. Vout equals Vin times R2 divided by R1 plus R2. Second, for question G, dividing total voltage Vin by entering current I1 gives the equivalent series resistance. Vin over I1 equals R1 plus R2. This proves that resistors in series simply sum together. This completes our full step-by-step solution.